Welcome back. Today we're doing 9-8 on power series. So we have a polynomial representation of some function. The new thing in this section is the polynomial will have an infinite number of terms. If it has an infinite number of terms, it will exactly represent the other function. So we'll start with a power series centered at 0. So the index for this one will start at n equals 0. We'll look at x to the n plus 2 power. So x to the 0 plus 2 power is x squared, x to the 1 plus 2 power, x cubed, and so on. If we wanted the same thing centered at, say, -4, or we'll do a different one. So this one will have an x to the n upstairs and an n factorial downstairs. So x to the 0 power is 1, and 0 factorial is also 1. 1 over 1 is 1. If n is equal to 1, then we have x to the first, but we want to center that at -4, so instead of just an x to the first, we would have x plus 4 to the first. And 1 factorial is still just a 1 in the denominator. N equals 2, x squared, but centered at 4, turns it into x plus 4, quantity squared, over 2. 2 factorial is still just 2. X plus 4 cubed over 3 factorial is 6. X plus 4 to the 4th over 4 factorial, 4 by 3 by 2 by 1, 24, and so on. So this is sort of an idea of how we center these power series at various x values. Next thing we want to look at is what's called the radius of convergence. So we'll say let f of x equal sum from n equals 0 to infinity, a sub n x minus c to the n. So just sort of a generic power series. The domain of f is the set of all x st such that power series converges. So notice this will always converge if x is equal to c. If we're centered at x equals c, c minus c is 0, 0 to any power is 0, add up a bunch of zeros, and your sum is still 0. So in general, there's going to be three possible cases for a power series centered at C. It's possible the series will only converge at that center value C. It is possible that there is a real number R greater than 0 such that the series converges. Absolutely. For the absolute value of x minus c less than r. And diverges for absolute of x minus c greater than r. It is also possible that the series converges for all x. And they are stipulating absolute convergence there. So either it converges only at one value at the center. It's possible that there's a range of values where the series will converge, and it's possible that you can't miss, it converges for all values of x. R is called the radius of convergence. So all x values where the series converges is the interval of convergence. Okay, so we'll start with an example of this where we're asked to find the radius of convergence. So this one, our index starts at 0, goes to infinity. We have 7 by x minus 6 quantity to the n power. So we'll start with the ratio test for this one. So we'll take the limit as n goes to infinity. 7 by x minus 6 to the n plus 1 over a sub n, 7 by x minus 6 to the n. So that is the limit as n goes to infinity. 7 by x minus 6 to the first, x minus 6 to the n, over 7 by x minus 6 to the n. So you get some nice, pretty cancellation happening there. So the goodbye to our 7s, goodbye to our x minus 6 to the n's. So we have the limit as n goes to infinity of x minus 6. Let me kind of flip over here. Run out of real estate there. So remember, the ratio test says it converges if that ratio is less than 1. So x minus 6, we want to be less than 1. So then here our radius of values where that's true is going to be 1. Now a quick little aside on some of these. For this section, x minus c to the 0 is defined to be 1 even if x is equal to c. So even though that would be 0 to the 0 power, we just use a little definition there. Similar to how in factorials we define 0 factorial to be 1. And a lot of our theorems are efficient, more effective that way, even though this one doesn't fit with the pattern of the others. If we define it that way, the math holds up. So this next one, we're going to find the radius of convergence. So we'll go from 0 to infinity again. N factorial x plus 8 to the n. So again, we'll use our ratio test, which will take the limit as n goes to infinity of a sub n plus 1. So n plus 1 factorial x plus 8 to the n plus 1. And that's the top of our ratio, bottom of the ratio, a sub n. So n factorial x plus 8 to the nth. So hang on to our limit as n goes to infinity, and just a little fixing up. So n plus 1 factorial is n plus 1 by n factorial. X plus 8 to the n plus 1. Similarly, x plus 8 to the n by x plus 8 to the first. Downstairs we have our n factorial x plus 8 to the n. So some cancellation. N factorial over n factorial is 1. X plus 8 to the n over x plus 8 to the n is 1. So we have absolute value of x plus 8 is unaffected by this limit, so we can put it out front. Limit n goes to infinity of n plus 1. Now notice that is infinity. So this will diverge unless x is equal to negative 8. In that case, we have 0 times any other number is still 0. So in this one, r equals 0. So our radius of convergence is 0. So this is the case where we have a single point, x equals negative 8. As opposed to here, we had the previous example, a range of values that would work. All right, so same question on the next one. Find the radius of convergence. So just have you kind of fill in those directions on your own. So from 0 to infinity. And we're looking at, let's see, x over n factorial. So again, we'll do our ratio. Limit as n goes to infinity. So x over n plus 1 quantity factorial over x over n factorial. So that's the limit. N goes to infinity. X over n plus 1 by n factorial. So just expanding out the n plus 1 factorial. dividing by a fraction, turn it into multiplying by its reciprocal. So x over x is 1, n factorial over n factorial is 1. So limit as n goes to infinity, 1 over n plus 1. So notice this one is completely independent of what's happening with the x's anymore. So this would go to 0 for all x. So here we have an infinitely long radius of convergence. This would work for any x value. This will always converge. So the next thing they have us work on is finding an interval of convergence. That's basically just putting r to work once we find r. Just a heads up on these. Once you find your endpoints, you must test them to find if we include the endpoints or exclude the endpoints. So it's not going to say that in the directions for each of them. It's just a little reminder for me to check on that. All right, so sum from, we'll go 0 to infinity. We'll do -1 to the n, x to the n, over n plus 3 by n plus 5. So first our quick little ratio test here. Notice here we're centered at 0. We're going to center this guy at 0. So we want the limit as n goes to infinity of a sub n plus 1. Absolute value says we can temporarily just ignore this -1 to the n. Absolute value is going to wipe it out anyway. So x to the n plus 1 over n plus 3 by n plus 5. And dividing by a fraction, turn it into multiplying by its reciprocal. Okay, so n plus 3 and n plus 5 will drop. X to the n plus 1 over x to the n turns into just x. So here, our radius is again 1, since this will converge if this limit is less than 1. So what this tells us, since we're centered at 0 and have a radius of 1, we have at least -1 to 1. Exclusive. We test the endpoints to find out if they are inclusive. So we just say let x equal -1. We'll see if we get to keep this -1 or if we leave it as an open paren. So going back to the original then, sum of n equals 0 to infinity, -1 to the n, there's our x, replace x with -1, -1 to the n again, over n plus 3 by n plus 5. So -1 to the n times -1 to the n will give us +1 to the n, and 1 to any power is still just 1. So then that is sum from 0 to infinity, 1 over n plus 3 by n plus 5. So that goes, we'll compare that to 1 over n squared. b equals 2, which is greater than 1, so this converges. And 1 over n plus 3 by n plus 5 is going to be less than or equal to 1 over n squared for n greater than 0. So the bigger one converges, so the smaller one must also converge. So this means we keep x equals -1. If we do the same thing with the x equal +1, sum from n equals 0 to infinity, -1 to the n times +1 to the n over n plus 3, n plus 5. On that one, we could just use our alternating series test. So 1 to the n will just drop out. So limit as n goes to infinity of 1 over n plus 3 by n plus 5 is indeed equal to 0. So condition 1 is met of the alternating series test. Condition 2 of the alternating series test, 1 over n plus 4 by n plus 6 is indeed smaller than 1 over n plus 3 by n plus 5. Bigger numerator or bigger denominator in the positives means smaller result. So this one converges. So we keep both endpoints. So this one, our interval of convergence then for this one is -1 to 1. We got to keep both endpoints. Both of them gave us converging series. All right, let's take a look at our next contestant here. This one we're going to go from 1 to infinity, -1 to the n plus 1, x plus 5 to the n over n 2 to the n. So ratio test to start us off, limit as n goes to infinity. The -1 to a power, if we're inside the absolute value, we'll just kind of neglect that. So x plus 5 to the n plus 1 over this n is replaced with n plus 1. 2 to the, again, and n gets replaced with n plus 1. Divided by a fraction, multiplied by the reciprocal. So n 2 to the n upstairs, x plus 5 to the n downstairs. So a little bit of simplifying where we can. So limit as n approaches infinity, absolute value of x plus 5 to the n, x plus 5 to the first, times n times 2 to the n, downstairs n plus 1 by 2 to the n by 2 to the first. So multiplying with the same base, we add our exponents. Same thing was happening upstairs. And then see what canceling you can get done. It's a good idea to close those guys as well. Okay, the n is what's changing here. The x is not changing, so x gets factored out. So x plus 5 inside of absolute value by the limit as n goes to infinity. Let's see, what's left upstairs is an n, downstairs is a 2 by n plus 1. We can even factor that 2 as well. So half absolute value of x plus 5 times the limit as n goes to infinity of n over n plus 1. So then we want our half absolute value of x plus 5 to be less than 1. So absolute value of x plus 5 less than 2. So here our radius is now 2 units wide. Notice also that the x plus 5 here tells us that we are centered on x equals -5. So we go 2 units in either direction. So for centered on -5, 2 units left, we're at -7. 2 units right, and we're at -3. And then we move on to test the endpoints to see, does it stay like this, or do we get to keep one or both of these endpoints? But we know we have at least this open interval. Maybe we can turn it into a closed interval. So we'll go with a let line, let x equal, I'll just test the left one first, x equals -7. So we have the sum from n equals 1 to infinity, -1 to the n plus 1. -7 plus 5 is -2, so -2 to the n. And downstairs we have our n 2 to the n. All right. So let's see, we have the sum, n equals 1 to infinity of -1 to the 1, -1 to the n, -2 to the n over n times 2 to the n. So from 1 to infinity of -1 upstairs, 2 to the n. So -1 to the n, -2 to the n is +2 to the n times 2 to the n. Notice our 2 to the n's will drop. So we can just sort of factor this -1 since it doesn't have an exponent on it. Opposite of n equals 1 to infinity of 1 over n. So this, notice, is a p-series with p equals 1. This diverges. So we're not going to get to keep that -7. We can only approach it. So then we use our let line on x equals -3, see if we get to keep that. So sum from 1 to infinity, -1 to the n plus 1 power. -3 plus 5 is 2, so 2 to the n over n, 2 to the n. So 2 to the n over 2 to the n, those will drop. So now we have an alternating series. So we'll do the alternating series test. The first part, limit as n goes to infinity of 1 over n does indeed go to 0. So far so good. So make sure your terms approach 0 as n goes to infinity. Then you make sure that a sub n plus 1 is always less than a sub n. So -1, or my apologies, we'll do the positive version of it. So then we have 1 over n plus 1 is indeed less than 1 over n. Those two conditions are met, so that means this does converge. So we didn't keep the -7, we did keep the -3. So there's our interval of convergence for that one. Okay, so next up we have our differentiation and integration. This is, as you can see, one of the bigger sections that we do cover in Chapter 9. So theorem 921, f of x, sum from n equals 0 to infinity, a sub n, x minus c to the n. We're going to assume non-zero radius of convergence, so it's not just a single point. Then on the interval c minus r to c plus r. So center, go left r units and go right r units. So on that interval, f is differentiable. So f prime of x, and this one works kind of the same way it did back when we were working with just regular polynomial functions. So if you're differentiating, this exponent is now a factor. So we have some from still 0 to infinity, n a sub n x minus c to the, instead of n power, n minus 1 power. And integral of f of x dx also works kind of the same way. Sum from n equals 0 to infinity. So now our exponent goes up 1 instead of down 1. And an n plus 1 downstairs. And then we have plus some arbitrary constant. All right, so let's put that to work for us. So f of x, sum from, we'll go on this guy 1 to infinity, negative 1 to the n plus 1, x minus 2 to the n over n. So we're going to find r for f of x, f prime of x, and integral f of x. So first the radius, limit as n goes to infinity.